I see more and more people are joining. Maybe we are ready to slowly start. Hello everyone and welcome to our 6th Teesmat webinar. I am Agata Papot and I'm project manager at EBN, the European Business and Innovation Center Network, and I've been supporting the organization of the Teesmat webinar series with the service providers who will present the validated characterization techniques and user cases. Today we have the pleasure to host the expert Odile Capron from VITO. She will present a session on battery physics-based modeling, fundamentals and methodologies. Odile will be leading the main session of the webinar, but if you have any questions or comments during her presentation, please feel free to share them in the chat box because we will have a Q&A session right before the end of the webinar. Just before we get started, I would like to give the floor to my colleague Dimitrios Zarvalis from CERT, Work Package 5 leader of Teesmat, who will give us some background information about the Teesmat projects. Dimitrios, the floor is yours.
Hello, good afternoon to you all. Welcome to our webinar. I believe this is the 6th or the 7th one. This is organized from the Teesmat project. I will very briefly introduce you to the Teesmat project. Usually this introduction is given by Fabienne Perdue, our coordinator from CEA in France. However, he's not available today, so I will try to very briefly present you our project. This is, as you see in the title, it is about an open innovation testbed for electrochemical energy storage materials. Odile, could you please go to the first slide, the next slide? Yes, this is the one. This is actually a test bed for electrochemical energy storage materials, for battery materials. This project was realized 3 and something years ago, started, and the drive behind this was that, as you know, the European battery market is growing fast. It is nearly 25% per year. And it was one of the top priorities of the European Commission to produce and to come up with a competitive battery value chain in Europe. So it is of course realized that to come up with this value chain, a battery value chain, you need a solid system for the characterization and understanding of all the processes that are involved in the battery development and operation and usage. So it was identified that this test bed was needed and was created under the name of the Teesmat. So at this project, we are offering advanced techniques that are developed or have been developed within different EU research labs and companies. Then can you go to the next slide, please? So our aim was to provide an easier access, a simplified access to an array of characterization techniques and services in order to solve problems that with respect to batteries that exist in the companies that are working with electrochemical storage, energy storage materials. So our main tasks was first to set up this test bed. This was the first phase, where we collected all the characterization techniques. Some of them were needed some advancements or needed developments. Some were already developed. Of course, they are all very innovative characterization techniques. And the second phase was actually to demonstrate these techniques on actual cases, on actual problems that partners, companies that are participating into the project are describing them to us. At the next phase that is coming now is to ensure the growth of this OITB, of course, the sustainability and actually the financing of it. And the next slide. So our project initially involved 8 service providers and 10 service users. We have 2 categories of partners. The service providers are research laboratories or companies that are providing research and providing techniques regarding the materials chemistry, morphology, structure, performance, as well as modeling tools. And initially we had 10 service users, then now we have more of them, and we have worked in more than 30 user access cases. These are actually what we call the problems that these companies are facing. Of central importance in our project is the database, where we collect all results regarding the samples and the tests that have been done. And we have a strict access control into that, where, of course, to secure the confidentiality issues where these exist. And the last slide to tell you where we are now. Actually, we are nearly to the end of the project. The first 2 phases are nearly to the end. Of course, we have developed the set we have set up. We have more than 33 or 34 characterization techniques now. Some of the techniques have not been validated. Some of them have new techniques have entered into our array of techniques. In this test phase that are now is ending. We are going to end this phase of the testing in August 2022, and we will start with a new phase after the end of the project, where it is actually the commercial activity, where our external service users, the companies that the future customers, what we call them, will come and solve problem, of course, at a cost. And we are also looking to incorporate external service providers that they have the potential also to contribute to our characterization platform. And I think this was the last slide about the Teesmat. Yes, thank you. Now Bill will explain you about the modeling activities we offer in the platform.
Thank you, Dimitrios. Odile, if you are ready, the floor is yours.
Okay, thank you. Thanks a lot. So here, first of all, to begin this presentation, so you can see the table of content. So first of all, a brief introduction about the physics-based modeling. Second, so an overview of the different kind of physics-based models. Then followed by some methodology overview, so in the framework of physics-based models. Also, an overview of the parameters that are involved in the physics-based modeling. Then the sensitivity of these parameters with regard to the modeling outputs. And also the different kind of simplified models. And we will also go through coupled thermal models, so physics-based model coupled with thermal modeling. And we will have an overview also on aging that can be coupled with physics-based models. And we will end this presentation with a conclusion about these physics-based models. So as Dimitrios mentioned in the Teesmat project, there are some modeling activities for different customers of the Teesmat platform. And so the content is linked somehow to what is done, so applied, followed as methodology and fundamentals that are used in the project. So first of all, as I mentioned, so the introduction, so about physics-based models. So what are these kinds of models? So basically it's mathematical models. So they are used to simulate the physical and electrochemical process occurring inside the batteries. So mainly the electrochemical reaction occurring in the batteries. That can be any kind of batteries. So it can be lithium-ion batteries or sodium-ion batteries. And it's really useful when it comes to understanding and design of these batteries. So with this, we can here, so you can see on the figure. So this kind of physics-based model can be used in order to investigate behavior of batteries at different length scales. So it can be from atomistic level to battery cell to battery module to battery pack level. So it covers a wide range of levels. Here also, with regard to this physics-based model, so it's important to mention that yes, they are based on fundamental physical and chemical equations. So as I mentioned, to translate the behavior of the batteries from the electrochemical point of view. So it helps to understand what is really happening in the batteries at different levels. So at the level of the electrodes and the full battery cell, and also at different levels in the different stage in the lifetime of the battery. So we can use it in the beginning to understand for the design, and we can also further use this model for the understanding of their aging. Although it should be mentioned that this kind of model requires high computing power. So due to the complexity of the equations that they are using and involving, and due to the large set of input parameters. And this is in comparison with empirical models, for example. And yes, also with regard to a comparison to, let's say, empirical models, so experimental based models. So yes, they are quite also used in the literature for modeling of batteries, although they are quite domain specific design. So they are working within the range of the experimental on which data set on which they are based. So therefore, that can be seen a bit as a bottleneck for this empirical models, whereas for the physics-based model is based on equations, so it's not really linked or limited by the amount of experimental data we have. So this was for the introduction. Now, if we look, let's say, about the different categories of physics or electrochemical based models. So what do we have? As you can see in this organigram, so we have two, let's say, branches of physics or electrochemical based models. So the first one, so you can see below, so the SPM, so the single particle model, it's kind of a physics-based model taking into account the internal structure of the battery cell being simplified. And we have also an extended version of this single particle model with this SPME, so taking into account the electrolyte. On the upper branch of this organigram, we can see the P2D, so pseudo two-dimensional model. This is also categorized in two different kinds of sub-models, let's say, the full, so where we do not have any simplification, and a simplified version of this pseudo two-dimensional model. We will see later on in the presentation why there would be a need for simplification of this model. So on the top here, so you can see that the pseudo two-dimensional model in the full version is of use and of high interest when it comes to cell design optimization. So let's say we have a manufacturer, or we have in the laboratory given electrode materials, given also electrolyte type and separator, and we want to assess about the behavior of batteries that would assemble or that would gather these components. So what would be the behavior of batteries, including this kind of materials, without having to test these batteries beforehand. So that can be really helpful in order also to investigate different kind of of cell component in a battery cell. So then the second kind of pseudo two-dimensional model, so the simplified, you can see that with the simplified version of the pseudo two-dimensional model, combined or not combined, but also along with the single particle model, taking into the electrolyte. So all these kind of models are widely used in as well as offline or online application. So it means the following. So these physics-based models are able to predict the state of charge of the battery cell and its electrode, so which is really important also when we think about, let's say, for fast charging, for the anode control charging, to be able to track and to predict the potential of the negative electrode. But these models are also able to predict and to give insight on the degradation mechanisms that are occurring in the batteries when it comes to the aging of the battery cells. So here, the state of charge of the battery cells. When it comes to, let's say, application, so when we want to use this physics-based model in BMS, mainly we use a single particles model or pseudo two-dimensional model in the simplified version. It can be also run offline for given application, but we will see later on in the presentation that embedding these models in the simplified version, but at least considering the different electrode components and battery cell can be of high interest in order to monitor the battery pack. So now the first, as I mentioned, so the single particle model, the SPM. So what does it represent? In fact, it's, as I mentioned, it's a simplified representation of the internal structure of the battery cell. And it is based on two assumptions. So first of all, it considers that each electrode is represented by two spherical particles. So we will have here, as you can see on the schematic, on the left side, we will have so a single particle representing, let's say, the negative electrodes of the battery cell. Whereas on the right side, you can see we will have a particle representing the positive electrode of the battery cell. So in these particles, there will be the intercalation and the intercalation of the ions, can be lithium ions or sodium ions, during the charge and discharge of the battery cell. But important is to mention that here the electrolyte is not considered. So we assume that these ions are moving from one particle to the other one. And in between, so the medium, let's say, the electrolyte is not considered, and variation in the electrolyte concentration and in the potential are thus ignored. So why would it be interesting to use this kind of single particle model, so SPM? So you can see here, sorry, that's as I mentioned, it's based on simplification on the representation of the battery internal structure. So that means we will also reduce, let's say, the computational power needed to solve these partial differential equations. So the mathematical model will be less power demanding, let's say, and the results will be obtained also faster. Although at below low current rate, so let's say below 0.5 C current, the electrolyte can be assumed constant, so that's really of application. And also, as I also mentioned, this is kind of single particle model can be used and is used, in fact, for online set of charge estimation and lifetime modeling of batteries within the condition that we are working at sufficiently low current rates. So the cons, so why would it be, let's say, a bit limiting to use this kind of model? So as mentioned, so this, let's say, threshold, so this 0.5 current rate, charge or discharge, yes, below it's okay, but above we will have some limitation. So the representation of the internal structure just with two particles and not taking into account the electrolyte can be limiting if you want to really reproduce the behavior of battery cells. Here, that was for the single particles model, and for the pseudo two-dimensional model. Short introduction. So first of all, this kind of models were developed by originally from work of Newman and Teesmat. It was developed for the macroscopic porous electrode theory. It was aimed for battery applications. And later on, Doyle and Newman developed so a really popular lithium-ion physics-based model, which is also commonly referred as Newman model in the literature, and is based on the porous electrode and concentrated solution theory. So concentrated solution theory, because here, in difference to the single particle model, we are taking into account the existence of the electrolyte. This model was updated so recently with regard to the equation for the formulation and the electrolyte more specifically. But it's widely used. It's also what we use within Teesmat, within some case. So that's also quite relevant in case of say even commercial applications. But it's based on several assumptions that's important to mention, so that the porous electrodes, so the two electrodes are represented in the battery cell, but it's considered to be made of spherical particles. These particles are equally sized, so they have all, they are assumed to have all the same size. They are also isotropic, and also they are homogeneously distributed within the porous electrodes. Why do we mention porous? Because it's also indicating that we are taking into account two phases. So they will be mainly a solid phase, and the rest of the electrodes will be filled with electrolyte and also with binder. So these assumptions make this model to consider an homogeneous description of electrode microstructure. So that's also what is leading to smooth and uniform intercalation and deintercalation of lithium inside electrodes. So it's quite ideal case, let's say. But in reality, however, lithium-ion electrodes are very heterogeneous structure. So that's good to have in mind. So these assumptions also, as can be seen now, yes, on the graph. So that's what I explained. To have a good representation, and we have a negative electrode on the left side, positive on the right side, the separator filled with electrolyte, and in which the electrodes will be moving to which one electrode to the other. Similarly, now to what was presented for the single particle model. So what would be the advantage of using such kind of models? So in which case would it be of application? So these physics-based models are describing really accurately. It's a fact in the literature. We can see battery internal electrochemical reactions by means of partial differential equations. So if we want to mention also with regard to the previous slide, so what I mentioned about single particle model, so the threshold of 0.5 C. So here with this kind of models, we will have really high, good accuracy above 0.5 C charge or discharge rate. What would be the cons? So in fact, this model is even less simplified, or is considering the whole internal structure. So it means that there are a large number of partial differential equations to solve, and that make it a bit complex. And also with regard to the computational power, that's why I explained also in one of the slides in the beginning that this kind of pseudo two-dimensional model, when it comes to application in battery management system, it is often simplified in order to remedy to this computational, let's say, load, and that can be quite limited when we work with real-time applications. So now, just to have an overview, so what would be, in fact, all these partial differential equations that I mentioned and that are in use when modeling batteries with two-dimensional models. So you can see with this organigram, so on the top, we have an equation which is describing the lithium transport in the particle domain, so in the solid phase of the porous electrode. On the left side, so you have a set of equations that are related to the charge transfer kinetics, also in the solid phase, so of the porous electrodes. Below left, you will have so basically equations for the charge conservation. So yes, we know that by charging or discharging of the battery, there will be movement of ions and therefore also movements of electrodes, so that are generating current. And these charge conservation equations are split for both electrode space and electrolyte space, given the nature of porous electrodes. And on the left side, you can see so the lithium transport in the electrolyte phase. So this this equation will lead to the electrolyte, which is part of the porous electrodes and also part of the separator, separating both electrodes, and in which the ions are moving through to which from one electrode to the other. So you can see that it's kind of a complex equations. It's also to be considered always, as you see in the slide, so the plus and the minus, because in fact all these equations are double, so it's for both positive and negative. So when it comes to plus minus, so it's to mention that we have the same equation, one for the positive electrode and one for the negative electrode. Based on this organigram, it's also important to mention so that for the single particle model, so which do not take into account the electrolyte, so we will have already these two. So for the lithium transport in electrode phase and the charge conservation in electrolyte phase, that will be, let's say, removed, and that will simplify already the amount of equations, reduce the amount. So that's important to mention here. So these are the governing equations, and when we move forward, so the pseudo two-dimensional model with regard to the single particle model, it's also simplification. It's simplification of the battery geometry, and it's called pseudo two-dimensional for the following. So because we consider two dimensions. The first dimension, so it's the X dimension, it's at the macroscopic scale. So in fact, it's considered for the process of the, let's say, the movement of ions through the electrode space in the battery. And the second dimension, it's the air dimension, so it's in the direction of the radius of the particle itself. So, and yes, the particles which are host for the intercalation of lithium in the electrodes. So, as you can see here on the scheme, so that's what I mentioned. So the X dimension is, let's say, in the thickness of when we consider, let's say, a layer of positive, negative, and in between the separator and the collectors, where the air dimension is at the level of the active material particles. So by coupling these two dimensions, we call it like pseudo two-dimensional model. They have different scales, these dimensions, and therefore it's pseudo two-dimensional. It's important to mention also that with this pseudo two-dimensional modeling framework, we are able to model and to predict, let's say, the kinetics of the electrochemical reaction occurring during charging and discharging by the movement of ions. And also, therefore, the transport processes, so how my ions are moving through the electrolyte and also to reach the center of the active material particle. As well as we are able to capture the thermodynamics of the battery cells. So that's quite important. Also, if we want to be able to model the battery cell at different conditions and different kind of applications. But these models, yes, in fact, so they are based on pseudo two-dimensional model and partial differential equations. And how is it implemented or used in practice? So all these equations, so what we just saw in the previous slide, they are implemented via either finite difference methods, so FDM, or finite volume methods, like Lyon-Simba, it's a MATLAB P2D model, to cite just one among others, and finite element methods, so FEM, so it's like the commercial consolidate physics software. So there are different, let's say, means to implement this partial differential equation and to create a model and model battery cells. Now, when it comes to the methodology, so we saw so far, let's see, the different kind of models, the different purpose, when to use them, the different equations, so on which they are based. Now, when it comes to really simulations, we have all the tools in hands. My model, so you can see in the center of this scheme, so is considering all the equations and the assumptions that we saw in the previous slides. But for my model to deliver results or simulations, we will have to introduce some inputs. What are these inputs? They are basically parameters that are related to electrodes and cell level. We can cite among others that there will be electrochemical parameters. So for both, let's say, positive and negative electrodes, as well as for the separator in between, as well as for the current collectors at each electrode. There are a bunch of electrochemical parameters, so we'll see later in the presentation. What is also needed, required as input for this kind of physics-based model is the current density. So yes, it's an input for the model, so it will, let's say, translate how the battery, which is the condition under which the battery is working from the current profile point of view. And its current density is mentioned because it's at electrodes level. The temperature is also an input. That's also to be considered because we will see also later on that these electrochemical parameters, they are, most of them, highly dependent on the temperature. So they are not constant during operation if the temperature is varying. Now, on the right side of the scheme, what you can see, so the outputs. So the outputs level, we will have, in fact, as I mentioned, this model is based on the electrochemical behavior of electrodes. And we will have, so therefore, information that will be delivered by the model for the potential and the concentration, as well as the side reactions at these electrodes. At the cell level, the information that we will get from this model will be the voltage of the battery cell, the state of charge, the state of health, and the temperature. It's important to mention also that in this methodology of this way of working, we are always considering, whenever possible, to validate this simulation output at electrode level as well as cell level. And that can be of great use, especially also when I mentioned in the beginning that this kind of model can be highly recommended tool when it comes to cell design optimization. Now, so we introduced the models, we introduced also the equation, we introduced also just now, let's say, the different steps in the methodology when working with physics-based model. So here we can see on this table the parameters related to the different domains in the battery cell are summarized. So whether it comes to the electrodes or the electrolyte or the separator. We will have so several parameters to consider that will be as input of the model, but these parameters are in fact related to or sensitive to different levels. So the first would be the state of charge, the second one the temperature, and the third one the state of health. We can categorize the influence that state of charge, temperature, and state of health have on these parameters. So just to list them, I will not go through in detail of these parameters, but here it should be considered that for the electrodes, so all of them are in fact double for both positive and negative electrodes. And yes, we will go later on. Yes, so these parameters, in fact, we know now that they are assigned to different domains, and they are sensitive to state of charge, temperature, or state of health, depending on which one. But it's also important to quantify and to have an idea, let's say, of how these input parameters are influencing, in the end, the output of my model. This is called, and widely applied, let's say, sensitivity analysis studies. So what is parameter sensitivity? So it's basically a measure how my output of my model is influenced by my input parameters. So influence in the sense of varying the value of the parameter. So how will my simulation output vary? And why it's important? Because we could see from the previous slides that from the table, we have quite a bunch of parameters to have a determined value to start the simulations. And it's important to identify, to categorize which of my parameters should I really put the focus on, and which one can I just make it, let's say, a bit less accurate if there is no other choice, but to categorize them, that will really be of high help. So sensitivity quantification of parameters, there are many studies in the literature, and it's mainly depending, when we see the results, on the model structure, the applied input, and the method for sensitivity analysis, whether it's global method or local method. So it's good to have in mind, because depending also on the results that are presented in the literature and the results that one can get from its own, there might be some variation, and it's good to understand from where this difference can come from. It's also important to mention, let's say, that we have in this list of parameters interactions that are possible. So what does it mean? That some parameters, by changing their value, might have an influence on the behavior or under other parameters of the model. So, and it's also observed in this kind of non-linear models, non-linear physics-based battery models. So the interaction is also not to be neglected. And last but not least, so sensitivity analysis of physics-based battery models. So what I mentioned also before, I help when we want to increase the understanding of the model, because we will know also for battery cell optimization which of my parameters will help me to reach the given performance of which of the parameters we will have to adapt in order to reach the target. So it's improving in that way also the battery design, as I mentioned. As illustration for this sensitivity analysis studies, so you can see on the top figure, so there are in fact several studies that were compared between each other. So you can see, so DFN refers to the Newman, so what was also called as pseudo two-dimensional model. And it was scattered, so with regard to given parameters also, so the same that were presented in my table. And it can be seen that, yes, in fact, can range from 0 to 1, and that for high sensitivity, so we can see that it's the yellow parameter. That depending whether the method was local or global, we will have slightly different results. But it's also important to mention and to have, let's say, visually in head, so that these parameters, in fact, it's what I represented here in orange. They are linked to, or they might be linked to different regions of battery cell discharge curve. So you can see, let's say, for the beginning of the discharge, so this is in case of LFP graphite cell during constant discharge. And what are the parameters that will influence my curve, my simulation curve? So it will be the initial concentration of lithium in the positive electrode, as well as the electrolyte content in my porous electrode at the positive electrode, so my porosity of the positive electrode, and the diffusion coefficient of the positive electrodes. Whereas in the middle range of the discharge, we can see that it's mainly parameters so related to the negative electrode and related to the kinetics and the dynamics. So basically the diffusion coefficient of my negative electrode and the positive and negative reaction rate. So that kind of kinetics and dynamics related. And in the end of my discharge, so the parameters that will influence would be my initial concentration of lithium or sodium ions in my negative electrode and the porosity degree of the negative electrode. So when we perform simulations and we want to compare with experimental results, let's say it's good to have this in head. So now, just to have a bit of highlights. So far we introduced the different models that are proposed, the different equations, the list of parameters, categorization or distinction between sensitive and non-sensitive parameters. This was presented in the framework of physics-based model and pseudo two-dimensional model. But it was also mentioned in the beginning of the presentation that due to the high number of parameters, high number of partial differential equations and their complexity, it might be of good use to reduce somehow these aspects that would enable to simplify this model and make them of application for battery management system and real-time application. So to be used online, let's say. So this figure you can see in the middle of the slides. So yes, we have a lithium battery pack configured with several cells and modules. And to control them, we have a battery management system as developed by VITO. And this battery management system, in fact, so includes or might include different kind of models in order to predict the behavior of the battery pack and the cells, and can have as output different properties such as state of charge, state of health, and the temperature for the thermal management. In the curve, the battery management system, you can see on the top, so we have physics-based models. So with simplifications, it's possible to include this model and make use of this model in real-time applications. Among others, because we have also like VITO in us equivalent circuit models in use, and there will be also simple empirical models that can be considered when used for battery management system. Although, as I mentioned, so the limitation of the single particle model and the complexity of the full pseudo-two-dimensional model lead often to invest a lot of efforts to adapt this physics-based pseudo-two-dimensional model and to develop a simplified version of the pseudo-two-dimensional model, but to reduce this not at the cost of accuracy, but for higher speed and yes, for higher speed and decreasing the power required for the simulation. Now, so we've seen that this model can be also in the beginning coupled with thermal models, because as mentioned, some of the parameters are really temperature dependent. So it's not to be neglected that also when we will increase the current weight, there will be also increasing the temperature in the battery cell that might affect the behavior of the electrochemical process due to the change of some electrochemical parameters. So what we can see here, so you can see on the right side of the figure that we have, so let's see, the coupling that is made between the electrochemical model and the thermal model. So there will be a feedback from thermal model, so the temperature that is computed based on the conduction coefficient, so the environmental condition of the battery cell, and this temperature will then be used as input for the electrochemical model to have the variation of these parameters, the temperature, and these parameters then are involved in the partial differential equation that were mentioned previously. So we will have here a coupling that will ensure to model the battery cell thermal behavior as it best. So this is possible, but it should be kept in mind that additional parameters would be required or needed, such as the specific heat capacity, the thermal diffusivity, and the thermal conductivity of these battery material electrodes. So this will then increase a bit the computational power required. But these models are also widely used in the literature, and we are making use of them in the Teesmat project as well. And interestingly, we can upscale them to 2-dimension and 3-dimension. So here is just an illustration so that we can, in fact, with this model and this coupling, elaborate the potential of both positive and negative electrodes in 2 dimensions, and we can also have an overview of the temperature within the different layers of the battery cell. Now, when it comes to the parameters, so that's referring to the table I mentioned some slides ago. So here in this table, the different parameters that are dependent on the temperature are listed. So we can see that it's both kind of parameters related to the electrolyte or the electrodes. So yes, it's good to have always this taken into account in the model, if possible, because low temperature, as known, it increase the decrease in battery capacity, so it accelerates the capacity decay. And low and high temperature also accelerate the development of degradation mechanism. It was mentioned in the beginning of the presentation that this kind of models, taking into account accurately the electrochemical phenomena occurring in the battery, can help us a lot with regard to the aging prediction of battery cells. So here we come. So regarding to the aging. So in fact, we could see that electrical and thermal behavior change with aging. That temperature should be taken into account, and this table highlights, let's see, the parameters that are sensitive to the aging of battery cells. So it's also related to the electrodes and to the electrolytes. And we have here, so yes, just as a reminder that in case of model for real-time application for BMS, for example, it's really important to consider these parameters and possible variation because we will have this translated in battery cell potential, battery cell current, and surface temperature that can be monitored with the BMS. And these parameters, so what we can read as output of a battery pack, will be used for state of charge and state of estimation of a pack level. So by knowing what can happen and what would be the degradation mechanism occurring in the battery and which of the parameters would evolve, it can be of use to translate and to link them to what we can read as BMS output and the level of pack. So now with regard to the aging, so we can see, so on the left side of the slide, so is the representation of the battery cell internal structure. We consider here in the figure, so two porous electrodes. And yes, in fact, as you can see in the middle of the figure, so the electrode is represented. It's a nice figure, really, when we want to relate this degradation mechanism and to what is happening in the battery. So you can see on the left side, so we have lots of active material that is occurring. It's also along with pore clogging that can also occur. Active material dissolution. So yes, or we can then also make a link with the capacity decay of the battery cells and the surface cracking, and also lithium plating and SEI layer formation and SEI codes. So all these mechanisms, these are conducting to the capacity decay. So what we can measure at the battery pack level. And yes, to the next slide, here we can see this dependency, these links that can be made, first of all, between the cause, the roots of the aging and the degradation mechanisms. So all the mechanisms that that were among others illustrated in the previous slide, and the degradation modes, and in the end, the effect. So in fact, what we can get out of this graph is basically that, yes, most of the time, what we observe at battery pack level, or cell level, we have capacity fade, the capacity decay, and power fade. Okay, to what can it be related to when we try to investigate the bit like what is going on? So the loss of lithium inventory can be a cause, a reason of capacity decay, and loss of active cathode material. So these two. And with regard to the power state, it's also loss of active anode material, so at the negative electrode. So if we want to go a bit deeper, so yes, we know that it's occurring at the positive electrode, at the negative electrode, and there is also loss of LNA, loss of lithium inventory. And we can make a link then with the electrolyte decomposition, for example, of DCR code and lithium plating dendrite formation. So in fact, there are many degradation mechanisms, as was represented in the previous slide, that can be combined and lead in the end to together to the different cause. So time, because we are using the battery since a long time, or the high temperature, high operating temperature, because the current is really large, and yes, it's also for low temperature, but mechanical stress, even when we talk about the silicon, let's say, particles or the electrode particle cracking. So this is, yes, an overview, and it's what is in fact behind what we have as output from the BMS. So I see the time. So this is my last slide for aging. So you can see, so in this graph, so there will be different mechanisms and different, let's say, way to implement them in the model. And this is just output of simulation. So it was only single particle model. And we take the loss of active material and SEI is yeah, for the solid electrolyte interface. So in fact, when we try then to implement this mechanism, and we corroborate with the experimental results, so we can see that the full plane lines are the simulated results, whereas the dots are the experimental data. So the amount of experimental point for the capacity in function of the cycles. And that's really interesting to see that, yeah, first of all, for most of the conditions, so the implementation of this mechanism, thanks to the fact that this model is physics-based and we implement the electrochemical properties and reactions in the battery cell, we are really able to follow and to predict already the trend of degradation and aging of battery cells. When we look a bit further, so it was mentioned that this kind of models are also in use in BMS. And it's really important also what they can bring as added value, because we can see that when we see if we use this, let's say, this physics-based model implemented in BMS, and then we will use them optimally so that we will reduce at different level the impact of the aging mechanism, of the degradation mechanism, we can significantly increase the lifetime of the battery by decreasing the loss of capacity through time. So you can see, so the yellow one was a physics-based model used for let's say predicting the optimal operating of the batteries to increase the lifetime and reducing the capacity loss. I come to the conclusion now. So physics-based modeling, yes, we talk about in this presentation. So it's mathematical tools to translate the electrochemical behavior of batteries by means of partial differential equations. It's possible and is of use in BMS, so for embedded model. It allows for the prediction of a battery behavior when it comes to cell design optimization. We want to see the behavior of electrodes combined with separator and different components. And it can also predict the state of charge of battery cells and then extend it to module, and the temperature as well, cells extend to module, and also have an insight of what is happening in my battery cells when used, and what is leading to this aging. So by understanding better this aging mechanism with this physics-based model, we are able, as showed in the previous slide, to increase the lifetime and therefore to decrease the capacity decay while making optimal use of these batteries. Although this should be always kept in mind that this kind of physics-based model, it has a cost. It uses and it involves a wide set of parameters. And yes, most of the time it's quite good to have in mind that this model requires quite a lot of computational power. So therefore, the simplification that are mostly done in practice. And also, with regard to the last slide, what I mentioned in the last video, let's say, we have comparison of experimental data and simulation data. And this kind of physics-based model, they are able to deliver really good results and also to lead to better, let's say, improve ratio of use of the battery cells and their efficiency, but it needs quite a large data set of experimental data. So here just the reference, so you can see in the presentation there were always some numbers into brackets just to refer to the reference of the figures and the literature. So yes, I see now the time. Hope that you could enjoy the presentation. Thank you, Emikis, for your attention and for your.
Thank you, Odile. Thank you very much for your presentation. It was a really interesting one. And I'm seeing some of the participants just shared some questions in the chat. Maybe I can read those to you.
Yes, sure.
So, and I also invite the participants to complement if the question indeed is not complete. So, one of the first questions from Emmanuel, it was, do you somehow integrate separator into the model?
Yes, so we consider the separator indeed, and the different properties like, let's say, the porosity, the thickness. So these are really the parameters related to the separator. So we consider it indeed.
Okay.
Sorry, the question was early in the presentation. It was about the single particle model, but after the pseudo 2D model, you implemented the separator. Yes, indeed. So for the a bit fast, sorry. Yes. So maybe you have a slide number so that I can refer to. So this one, yes. Okay. Yes, indeed. So it was mentioned here. So let's say, for example, the concentration is considered constant and potential are ignored because, yeah, we just consider these two particles. So yes, the electrolyte in between is not considered, neither the separator. So I don't know if it answers your question or what was the purpose of your question.
I think, sorry?
Yes. Sorry, did you ask something? I lost it. No. What was the purpose of your question? Of it answer your question if we consider the electrolyte separator? Yes. Okay. Thank you.
So Odile, then we got another question. I'm gonna read it to you. Do the physics models consider the influence of electrode porosity distribution on final discharge capacity?
Yes, that's a good question. So the electrode, was it mentioned? So the electrode porous
Hi, maybe I can explain.
Yes, yes.
I just saw one, you consider a factor just to take the value of porosity as a single value rather than a distribution. So I was wondering, because in reality, it's very hard to think of electrode having a single value of porosity. So
Mhm.
how would you consider the fact that the electrode with different porosity influence the final capacity of the cell? Just considering the physics model, I mean, just that's what slide number 5. I mean, yeah.
Yeah. So yeah, in fact, we consider that the porosity, so it's it just applies the same. So it's constant, but you are mentioning about different values for the porosity depending on a few electrodes.
Depending on the active material porosity, maybe, or the coating itself.
Yes, for now, so what we are using and also investing in Teesmat is considered just a single value, but for sure it can be really interesting to have like even in function of the coating of additional variation included in this value and not just consider as constant. But okay, it will also increase, of course, the computational time and the load, but that might be of interest, especially for the cell design stage. I think that would be quite relevant when you want to test different combinations of electrodes.
But let's say when you compare with the experimental data, do you think it's not, I mean, I'm not expertise, I don't have the expertise in the topic. You think it's not relevant to have a so high computational intensity just to consider this factor, because just by considering porosity as a single value, we can be having a very good correlation value, like.
Yes, indeed. For now, so what we are working on, and especially when you want to model commercial cells, yes, that should be enough to consider concern. But at the cell design optimization level or for stage development of pre-materials, that would be of interest, of sure.
Okay. Yeah. Thank you.
Okay, so then we got another question from Anthony von Vaqueros that is thanking you for the presentation. And the question is, are you planning to work also on 3D physics-based models at the particle electrode level? And do you see unique benefits on this?
Yes, indeed. So thank you for the question. That's also a topic of research and also covered in the literature to model really more atomistic level. I assume from the question and from particle point of view, let's say active material. For now in Teesmat, we are not doing this kind of modeling, so we are not going that deep. But yes, again, I think for understanding better, so the interaction of what is happening in the battery and insertion of these ions in the particles, that would definitely give an added value. And it depends, yeah, what is the purpose of the modeling, of course.
Okay. So more participants are thanking you for the presentation, and we have the last question. Is it possible to extract the parameters for a P2D model by fitting experimental cycling data?
Yes, so it depends which kind of electrochemical parameters. I don't know. Was there any example?
Yeah, so hi, maybe I can elaborate.
Yes.
So in the physics-based model, you fit in the parameters for electrode properties or electrolyte and diffusivity and other things. And one challenge is always to get these properties accurately for different grade of materials, especially let's say if a cell manufacturer or a material manufacturer is manufacturing, they will not let's say have all these parameters measured for every material. Some of them can be. So I was wondering if it's possible that you have this P2D model and you at the end you dial in some dummy parameters, you get the voltage profile, and then you train this model using the cycling data of different materials or of the same material with different cycling, and then backtrace the parameters to fit these electrode, electrolyte, and other parameters.
Yes, I think that yes, from the full cell point of view, I think, can you see the slide now?
Yeah.
So it can somehow be related to the sensitive parameters. So in my opinion, the most sensitive parameters, it might be that you can track back so their influence or their value on the full cell battery voltage. Although to determine a specific value, or you start with a given value that you know, okay, that's in that range, and then you can see. But starting with no idea of the value, that would be quite difficult. But if you have an idea of the value and you know in which region
range
parameters are acting, that could be possible. Like when we do simulation, we compare with the experimental, and we know which of the parameters we should adapt. But that is always starting with the given values, of course.
So maybe I can ask a follow-up question. As you mentioned the sensitive parameter, so is it a possibility that you start with, let's say, one set of controlled experiments to determine these parameters for your material? You have the agreement of model with the experimental data, and as you move forward with different grade of material or designing more cells, you can assume that the parameters or the less sensitive parameters will remain the same, and the sensitive parameters you either measure it or backtrace it, something like that.
Yes, indeed, we can then categorize in that way. But yeah, that's anyway challenging, and also what I mentioned during the presentation, the accuracy of this value can have somehow, depending on the sensitivity, quite huge influence on this simulations. That's all the challenge. But you're right, that can be an approach.
Yeah, because I hear these a lot of times, that parameter extraction of P2D model from machine learning, but I wanted to know from your point of view, how feasible is this approach, and what are the loopholes? So
yeah, and as you mentioned, it's in the scope of machine learning. So yes, I guess from that point of view, that's quite convenient to get directly these values extracted from the experimental. Although it should be mentioned that from our activities within Teesmat, we are using most of characterization techniques at electrode levels to derive these parameters, and that's maybe if you have a source or reference where they did it that way, then okay, that could be a good input for the machine learning, but always based on value that was determined experimentally at the output levels would be convenient.
Okay, thank you.
Thanks.
Thank you. So I see there is the last question in the chat. Just Nicholas wrote something. I don't know if you have time now to reply to this extra question. Okay, I can read it for you. So if you have 3D electrode morphology data, for example, nanotomography or FIB-SEM, etc., would you extract parameters such as tortuosity from this data, or would you prefer to determine these parameters from other experiments?
Yes, 3D tomography, indeed, yeah, that's a good question. It's possible, and also it's related to a previous question. So the modeling really of let's say the 3D geometry of electrode, porous electrodes. Yeah, that can give an information, but it should be kept in mind, yes, first of all, the accuracy that is required for these parameters. If it's porosity, yes, it's quite influencing parameter, but and also the time, I don't know exactly from the time point of view how fast can it be to get these values from this experimental compared to what we are using now. Let's say for the electrode porosity, like mercury porosimetry, or based on analytical formula, or yeah, I don't know. It also depends on the time that and the budget you have allocated to determine this, but that would be nice to to know if it can be of any added value. And sure. I
Okay.
don't know if it answers the question.
I think so, because I don't see any other reply in the chat. So I guess we can close today's session, since I don't see any other reaction from the participants. I would like to thank you, Odile, for your presentation and for accepting our invitation today. And I also would like to thank all the participants for this very nice and interactive session. I wish you a good afternoon, almost evening, and see you for the next appointment for the next Teesmat webinar. Thank you, everyone.
Thank
Bye.
you. Bye. Have a nice
Thank
day.
you, Odile. Bye.
Thank you very much.
Bye.
Bye.